Started then. Yesterday we went over partial fractions. And we went through a couple starter questions where we looked at how we normally combine fractions and how we get a common denominator and stuff like that. And then we went through the idea of partial fraction decomposition. And what we're doing here is we're taking a fraction and we're breaking it into the parts that it came from, which seems like a really weird thing to do. And it is a very weird thing to do. The only time that I've got a bachelor's degree in math, a master's degree in math, and the only time that I've ever done this is when I'm doing a specific type of calculus problem, okay? So if you plan on taking calculus, if you're going to be an engineer or something like that, or you're going to be a doctor and you've got to take calculus for your pre-med program or something like that, you are going to see this again, and it's going to be very helpful if you can remember how to do it, okay? So basically what we do is we factor the denominator completely. Okay? We break the fraction into as many parts as factors as we have. We do one part for each factor in the denominator and one part for every one of its repeats. And we saw one with a repeated linear factor yesterday. We put undetermined coefficients, so we put big capital letters on the top to represent the numbers that could have been there. And then we go through and we clear the fractions. That will make an equation. And then we use one of three techniques. We're going to use convenient numbers, or we call them convenient zeros sometimes. We're going to use a system of equations, and a system of equations is your fallback. It will always work, okay? Not the fastest way, but it will always work, okay? And then the cover-up method, which I said you could try with a couple of these. It's interesting that it works, but the hard part about any shortcut is you've got to remember exactly how it works, and it would be really good to understand why it works that way. And the last step is really easy. Once you find those big capital letters A and B and C and so forth, you just come back and you rewrite the original fraction as its parts. Okay, don't forget that. A lot of people kind of get relieved once they find out what A is and what B is, and then they stop right there. You want to go back and you want to write the original fractions. Okay, we made the point that you can't do partial fraction decomposition unless we've got a proper fraction. So if you have an improper fraction, you can do long division, and then you're going to have this piece plus a proper rational fraction that you can go ahead and do partial fraction decomposition on, okay? So we did that problem right there. It turned out to be pretty easy. We did that 3 different ways, you'll remember, okay? Quite a mess right there. And then we did this problem right here, also relatively easy, okay? We ended up with fractions in the numerator, and we said that was pretty much okay. And then we did this problem right here, and we talked about how we've got a factor of x, so we've got to have a part with x in it. I've got a factor of x minus 1 quantity squared, so I've got to have a part with that in it. But we could have had a part with just a plain old x minus 1 that would have kind of gotten swallowed up in this one right here. And that's why we looked at that starter question, okay? Each numerator is 1 degree less than the denominator. So this is degree 1, that's degree 0, so a plain old number. Degree 1 for a factor, so degree 0 for a numerator, plain old number. And again, don't get caught up in the fact that this is squared or cubed or raised to the 4th power. Okay, it's whatever the degree of the factor is, and this factor is still degree 1, so this is degree 0. Okay, that's a pretty common mistake. And then we went through and we solved that, and we found all 3 of them. We did have to write a little bit of a system of equations, or in this one, we actually picked another nice number to plug in because we only had one number left to find. We found A, we found C, we were looking for B, we plugged in one more number, and we got an equation that we could solve with what we had. Okay, any questions? Okay, so we've got 1, 2, 3, 4 problems to do, and we've got about 40 minutes to do it. Think we can do it? I think so, okay? So a lot of times with complex ideas like this, it takes a while to get the idea in your head, kind of let it cook there for a while. It may have been totally confusing yesterday, but I'm hoping now we can go through this and we can see, all right, I can see where that would work, and hopefully it'll be a little bit easier. So let's take a look at this problem right here. This one has some nice advantages. It's already factored, and most of the ones that you have are already factored, so that's kind of good. They're both linear factors, okay? So we're going to take this and we're going to write it as one piece for the factor of x plus 2 and one piece for the factor of x minus 1. I'm going to put parentheses around each one of those. I'm going to look at the factor in the denominator, figure out what its degree is. This is degree 1, so what degree is the numerator? Degree 0, so it's just a plain old number, right? So this is an A. Same thing here. So that one's just a B. So the whole point of this is I want to figure out what A is and what B is, and then we're going to write, okay, I've got this piece and this piece. This one's going to have an x plus 2 on the bottom, and this one's going to have an x minus 1. I need to find those numbers right there, and I'm going to put a big circle around that, and then I'll be finished with this problem. So that's what we're after. So the way we solve this is we multiply this equation, because these two things are equal to each other. We multiply this equation by the factors in the denominator. So this gives us a 3x on this side. This gives us an a and an x minus 1. This gives us a b and an x plus 2. Do I have any convenient numbers to plug in? Yep. Okay, the 0 for this one is -2, and the 0 for this one is 1. So let's let x equal -2. And we're going to plug in a -2 wherever there's an x. So this is going to be -6. Question? Right here? No, because when I multiply this by x plus 2 and x minus 1, the x plus 2 cancels and the x minus 1 cancels, so that leaves a 3x. Okay. When I multiply here, the x plus 2 cancels with the x plus 2, so there's the a and the x minus 1. Does that work? Okay. Good question. Anything else? Okay. When I plug in a -2, I get a -2 minus 1. So that's going to be -3. So this is -3a. And what happens here when I plug in a -2? You get a 0. So do I even need to write it? No, it makes the whole thing equal to 0. So all I'm left with is this simple little equation right here. Okay? And that's why we call that a convenient 0 or a convenient number, because it makes it, I mean, an answer just practically drops out. So this tells us that a is equal to 2. Any questions? Okay, I've got another convenient number to plug in. I'm going to plug in a 1. If I plug a 1 in here, I get a 3. If I plug a 1 in here, I get a 0. So I have 0 times a, so that's gone. Over here, I have a 1 plus 2. That's a 3, so I have a 3b. And I have a nice simple equation to solve, so I end up with b equals 1. Okay, now, if you can do that, you can do one of the problems on the test. So if you have any questions, please don't be bashful or shy or ashamed in any way if you're not quite sure how that works. Please ask a question. Are there any questions there? Pretty easy, right? Okay. So I'm going to come up here, and the a was over the 2, so I'm going to put a 2 on here, and I'm going to put a 1 on here, and that right there is the answer. Now, yesterday, Raymond asked a question. He said, well, what if I wrote it down this way? What if I wrote x minus 1 first and then x plus 2 first, and I put an a here and a b here? If you did that and you went through and solved, guess what you'd find out a is? A would be 1 and b would be 2. Okay? The correct number is going to end up on top of the correct factor. Okay? So the order you do them in doesn't matter. It's that you do it right. And doing it right means figuring out what the factors are, making a part for each one of those factors and its repeats, and then going through this process correctly. Any questions? Okay. Okay. That's a pretty easy one, isn't it? Okay. I want to show you something else. Okay, you don't need to write this down unless you really want to. I just want you to watch. Okay, another way to solve this one, because that system of equations idea is such a valuable technique, I want to show you what we've got here. If I were to distribute through, I get an ax minus an a over here. And if I distribute through here, I get a bx and plus 2b right there. So what I'm saying here is I've got a polynomial on this side, and it should equal the polynomial on this side. But this looks like a really ugly polynomial. So what we're going to do is we're going to collect the like terms. Okay. On this side, I've got an ax and a bx. So I'm going to factor out the x, and I've got an a plus a bx. There's an ax. There's a bx. I'm adding them together, so I'd have an a plus a bx. This is a plane number and that's a plane number. So I'm going to say the plane number is equal to negative a plus 2b. So I really have two terms on this side. I've got an x term and I've got a plain old number term on this side. Well, over here I just have a 3x. So I've got a 3x, and do I have a plain old number? I could put a 0 to save a place for it, couldn't I? And then what we do is we go through and we say, look, this polynomial over here has got to equal this polynomial over here. So this had better equal that, and this had better equal that right there. Now, this is a more complicated approach than what we did right here, and I said you should use this approach. If you have any convenient zeros to plug in or convenient numbers, I would use that technique. But I just want to show you how this works, because we're going to need to use this in just a second on a more complicated one, and that it's really not that bad. The logic behind it hopefully is pretty easy. So what we're saying here is this coefficient right here, 3, that goes on an x, should be equal to this coefficient right here that goes on the x. So that means 3 should equal a plus b. And it also means that 0 should equal negative a plus 2b. Okay, this is a system of equations. You can solve them by substitution or elimination. Are those things that you've seen before? So the cool part about this is it's already set up for elimination. If I just add those two equations together, I get 3 on this side. A minus a is 0, and I get b plus 2b, that's 3b. So what's b? B is 1. If I take this and I plug it in right here, I get 3 equals a plus 1, so that means a equals 2. So I got the same answers that I got before. I just did it a different way. Okay? And again, this technique is where we solve using a system of equations. We're basically going to get a polynomial on this side and a polynomial on this side, and we set the coefficients equal to each other. Okay? Any questions about that? You understand the logic behind that? You certainly don't need to do it two different ways. Okay? If you got done with the test in a half an hour and you had 20 minutes to check and you wanted to make sure you got them right, by all means, go ahead and do it another way and check and make sure you got it right. Okay, any questions? Okay, let's take a look at this one. This is a little bit more interesting. So on this problem right here, it's already factored. So I can break this into one part for each of these factors. So this is going to be x plus 1 plus, this is going to be x squared plus 4. And the reason I've got to keep that in x squared plus 4 is, does x squared plus 4 factor? Nope, certainly not using real numbers, okay? So remember the rule. The rule is, and you will have something like this on the test, so I'd be aware of it. The rule is the numerator is 1 degree less than the factor in the denominator. So if this is degree 1, the numerator is degree 0. That's a plain old x, or sorry, plain old a. The factor in the denominator here is degree 2, so the numerator is degree 1. That means it has an x in it. So this has got to be bx plus, it could also have a plain old number on it. So if you have a degree 1 polynomial, it's got to have an x, but it could also have a plain old number, a constant on the end. So if you've got a degree 2 factor, the numerator is going to be degree 1. It's going to be in the form of a number times x plus another number. Now, just like we talked about yesterday, maybe that's not there. Maybe it was just like a 7x. If it was just a 7x on the top, what will we find that c is? We'll find that c is 0. Okay? Any questions? Okay, so our goal here is we're going to write the answer something over x plus 1 plus something over x squared plus 4. This is what we're after. So let's figure out what these are. I'm going to multiply this by x plus 1 and x squared, x squared plus 1 and x squared plus 4. When I multiply here, I'm only left with a 1. When I multiply here, I'm left with an a times the other factor of x squared plus 4. And when I multiply over here, I'm left with bx plus c times the other factor of x plus 1. Okay. Is this going to be harder than the last one we did? Yep. Can somebody tell me why? There are a couple reasons. How many undetermined coefficients do we have? 3. That's going to make it harder. How many convenient zeros do we have? Only 1. So we're only going to get one of the answers to drop out immediately, and then we're still going to have 2 more to find. Okay, that's going to be a bit of a pain. So let's go through and do this. If I do have any convenient numbers, let's go ahead and plug them in. What is the convenient 0 on this one? -1. So if I plug in a -1, oddly enough, it doesn't change that one at all. That's going to make this -1 squared plus 4. So this is going to make this 5a. If I plug in a -1 here, that makes this 0. 0 times whatever this is going to be 0. So I don't need to write that anymore. So this tells me immediately that a is equal to 1/5. So I have one of the undetermined coefficients. Okay, now, here's how I like to find the others. Okay, you could plug in a 0 or a 2 or something like that and make some other polynomials, okay, make some system of equations. This is the way I like to do this, okay? So I'm going to go through here and I'm going to distribute through. This is going to be 1 equals ax squared plus 4a. When I multiply here, this is going to be bx squared plus bx plus cx plus c. You with me? Okay. Any questions there? All I did was just take this line right here and distribute through. Now I'm going to collect like terms. So this side is a 1. I've got a couple of x squared terms. So I've got an a plus a b x squared. Start with a set of parentheses, write down that coefficient, write down that coefficient. So I'm done with those two guys right there. And I like to just put light slashes through each one of them. Don't scribble them out so at least you can still see them, but you can see what you've already used. What terms would I put next? The ones with x's, right? So I've got a b and a cx. So I'm going to put plus, set of parentheses, b plus c, x on the end. Done with those. And then the very last thing that I've got is these numbers right here. And again, set of parentheses, for a plus c. Okay, now there is no doubt this is tedious. Is this very hard? Hopefully not. Okay, now watch carefully. This side is a 3-term polynomial. It's got an x squared, an x, and then a plain old constant term. This side over here doesn't have any x squareds. So we're going to put 0x squared. It doesn't have any x terms, so we're going to put 0x, and then it's just got that 1 sitting there. And then again, we're going to go through and we're going to look at it this way. That coefficient better equal that coefficient. This coefficient better equal that coefficient, and that constant right there better equal that constant right there. So we're coming up with a system of equations. We're actually going to have 3 equations from here. I've got 0 equals a plus b. I've got 0 equals b plus c, and I've got 1 equals 4a plus c. Any questions? Okay. Oddly enough, we are almost there, and it's not going to take much work to get there. Do we know any of our undetermined coefficients? We know a, don't we? So what if I did this? What if I came down here and I said, you know what, I know a is 1/5. If I take 1/5 and add it to b, I get 0. So if I move the 1/5 to the other side, that would be -1/5 equals b. Let's let me do a dotted one around that. So now I know the other one. Well, now let's turn to this one right here. Do I know either one of these? Yes, I do. I know what B is. So 0 equals negative 1/5 plus C. If I move that to the other side, I get 1/5 equals C. So now I have A, I have B, and I have C. Okay? Now, you don't need to use this one, but what I like to use this one for is what I like to call a double check. There's a lot of calculations to do here. There are lots of places where you could make little mistakes. If I take the numbers that are in this last equation right here and I plug them in and I get something that's true, I'm pretty darn sure I haven't made any mistakes. So this is 1 equals 4 times 1/5 plus 1/5. That would be 4/5 plus 1/5. 5/5 is 1. Did we get them right? Yes, we did. So we come back up here and let's write this down. Our goal was to write this as its parts. We've got A, let's find A, that's a 1/5. We've got B, that's a negative 1/5, so negative 1/5 x, and then plus 1/5. Okay, and remember I said it really doesn't bother me if you leave it in this format right here, leave it with a fraction in the numerator. If you wanted to factor the 1/5 out front and put a 5 on the bottom and a 1 on the top, that would be okay with me. If this were a test question, I'm totally fine with that. Okay? Any questions? Okay. Raise your hand if this is harder than you thought it would be. Okay, I see some half hands going up. That's totally okay. If you have a question when you're going through and doing these, I really would love it if everybody did great on this test coming up. So come and ask me a question. Okay? How many people think this is a little bit easier than they thought it would be? Okay. All right. And sometimes it's just how it hits you. Some people love this type of stuff where it's just, I don't care how much work I have to show. I just want to know I can get the right answer. Okay? It's a very tedious process. Lots of places you can make mistakes, but any one step isn't too terribly difficult. It's putting it all together that seems kind of tough. Okay? Lots of places to make mistakes, so be careful. Okay, let's take a look at this one. I'm going to give you a 30-second head start to write down the first step. This one clearly has some advantages. If you're not 100% sure what you should do, don't write anything down until I do, or hopefully you're writing in pencil. And I'm going to pick on Sven this morning. Sven, how many parts? How many parts do I need to write down over here? How many? Okay, Sven says 2. Raise your hand if you agree with Sven. 2. Okay? Anybody disagree with Sven? Ooh, 2, 3, 4, 5. 5 brave souls in the minority. Cameron, how many? There are 3 parts. Okay? Remember, there are 2 factors that show here, but one of them is repeated. So we're going to write a part for every one of its factors. So this is going to be x plus 2. This is going to be x plus 1. And its repeat of x plus 1 quantity squared. Remember, this is why we looked at that starter question yesterday. Maybe this is here. Maybe it wasn't. But if it is there, we better save a place for it so we can find what number goes on the top. If we only did the 2, the first one and the last one, we'd never find this one if it was there. And our answer would be wrong. Because our A, B, C's and stuff like that, we wouldn't find the right ones. Okay? Any questions? Okay, the next question is what goes on the top. So we figure out the number of parts by figuring out it's a part for each one of the factors, which we've got here, and its repeat. So 3 parts here, we got that correct. And then we need undetermined coefficients. Again, the rule is the numerator is 1 degree less than the factor in the denominator. Just the factor. Clearly degree 1, this is degree 0. Clearly degree 1, this is degree 0. What degree is the factor? The factor is degree 1. There's a little 1 sitting up there. We just don't normally write it. So what do I write on the top here? A c. Not a cx plus d. That would happen if this was that squared. Okay? Any questions? Okay. So our goal is to figure out what I put here. What do I put on the top of this? What do I put on the top of this? And what do I put on the top of this? That's what we want to find out. This right here will be our answer. Let's figure out what we've got. So I'm going to take this and I'm going to multiply it by each one of the denominators, or each factor in the denominator. This will happen every time. What happens over here when I multiply with this one? It just turns out to be what? Just the numerator, right? So I've got an x minus 3 equals, I've got an a, and what do I multiply it by? X plus 1 quantity squared. This one's going to be b, and x plus 2 definitely, and I only canceled one of the x plus 1, so I've got that. And then I've got c, and I've got an x plus 2. Any questions? Okay. How many undetermined coefficients do I have? I've got 3 undetermined coefficients. How many convenient zeros do I have to plug in? I've got 2. So 2 of those I'm going to find pretty darn quickly. Make sense? We're going to need to work a little bit on the third one. So what's the first number that I'd like to plug in? Let's do a -2. It's the first one that we come to here, then we're going to plug in a -1. So if I plug in a -2, this is -2 minus 3. This is -2 plus 1 quantity squared. Okay. Do I need to bother writing this one? No. Do I need to bother writing this one? No. Any of the terms that have this factor in them, x plus 2, I'm not going to need to write them because that's the whole point. It turned it into a 0. So this is a -5 on this side. This is a -1 squared, which is 1. So this side is just an a. There's my answer right there. This whole convenient zeros process is pretty darn convenient. The answer practically drops in your lap. Any questions? Okay. Would you do the next one? What do you get when you plug in a -1? Do that one. Find your answer. Check with your neighbor. Okay, have you got it? Did you check with your neighbor? They're not going to bite. Check with your neighbor, see if you got the same thing. Or see if you're on the right track. Okay, what'd you get? -4? Okay, so this is going to be -1 minus 3. Do I need to write this one? Nope, because it's got that factor of x plus 1. Don't need to write this one because it's got that factor of x plus 1. I do need to write this one. This is going to be c and -1 plus 2. Well, gosh, that's great because this is a -4 over here, and that's a c, so I've got the other one right there. So I know what a is, and I know what c is. Okay, now, I could go through and I could distribute through and all that sort of stuff like I did on that previous one. Okay, let me run back here. Remember on this one, we only had 1 convenient zero, and we had 2 more undetermined coefficients to find. Okay, so each convenient zero will give you an undetermined coefficient. Okay, if you've got 2 left, I think it's best to do this. Okay, if you only have 1 more left, I know what A is and I know what C is. I only have 1 more. And there's a very easy number that you can plug in. I would go ahead and do that. Okay? You can use this technique where we distribute through and all that sort of stuff, but that's going to take quite a bit of time. Watch what happens if I pick this convenient number. What would be the most convenient number to plug in? What's really easy to do arithmetic with? 1 is. What's even easier than 1? 0. Let's plug in a 0. Watch what happens when you do a 0. This side's a -3. This is a 1 squared. 0 plus 1 squared, so that's going to be an A. This is a 2. This is a 1, so this is 2B. And this is 2C. Wherever there's an X in here, you just put a 0. There's an equation. And what's nice about that equation, it has an A, a B, and a C in it, but what's nice about that? We know A and C. Okay? Any questions? So if I know A and C, if I know A is -5, -3 equals -5 plus 2B, and this is going to be -8, is that right? So this is -3 equals 2B minus 13. Move that over to the other side by adding 13, so I get 10 equals 2B, so that means that B equals 5. Got A, got B, got C. So we're going to write -5 on top of this. We're going to write 5 on top of this, and we're going to write -4 on top of this, and there's our answer. Okay. Any questions? Okay. Write down the parts there. This is by far the weirdest one. I don't think you have any that are this difficult on your assignment, but if you can do this one, I think you can do any of them. Okay, remember the rules. It's one part for each factor and their repeats. One part for each factor and their repeats. And I'm going to pick on somebody in just a second to take a guess at what this is. How many parts? Logan, how many parts? 2 parts. Logan is correct. 2 parts. Tammy, can you tell me what goes under this one? X squared plus 4. Yep. And Brandon, can you tell me what goes under this one? Very good. Okay. Okay. This is just the repeat of that guy right there. Okay. Those are the 2 parts. Okay. Then the rule is the numerator is 1 degree less than the factor in the denominator. So this is degree 2. Nathan, what do I write on the top here? Plus B. Very good. Okay. Okay, this is a degree 2 factor. So Miranda, can you tell me what goes on the top of this one? Cx plus D. Okay? All right. So there's the setup. We've got the right format. I don't think I've asked, has anybody in here seen this before? Wow, totally new topic to everybody. I think that's the first time that's happened. Okay, so again, our goal here is we want to write something over x squared plus 4 plus something over x squared plus 4 quantity squared. That's what we're after. So here's going to be our final answer. We've just got to find the numbers that go on top here. The technique is the same. We're going to multiply by the denominator. This is just going to end up being the top, x cubed plus x squared. Over here, I'm going to have ax plus b times what do I write? Only one of them canceled. So there's still one of these stuck around here. So this is x squared plus 4. With me there? And then what cancels when we multiply here? Both of them, right? So what's the numerator? Cx plus d. Pretty cool. Any convenient numbers, any convenient zeros to plug in? Not a single one. Not one. Not one of these answers is going to just drop out at us. Or maybe it will. Let's distribute through. We've got to use that idea of that system of equations. So let's distribute through. I get x to the third, ax to the third. I get plus 4ax. I get plus bx squared. And I get plus 4b. And then I've got plus cx and plus d. Any questions? Okay, I think you'll be surprised how easy this is. This is actually one of the easiest ones in the notes. Okay, how many x cubed terms do we have? Only one, ax cubed. How many x squared terms do we have? Just one, bx squared. How many plain old x terms? This one here and this one here. So 4a and c. So again, put a plus, start a set of parentheses, 4a plus c, slap an x on the end. We've got those two taken care of. And then plain old numbers in the end, just this one and this one. So again, put a plus, start a set of parentheses, and write down what those numbers are with the sign in front of them. This looks awful until you write down what's over here. What's on this side is 1x cubed plus 1x squared. Any x's? So what do I write? 0x. Any plain old numbers? Nope. So I write a 0. And then we go through and match them up. Those two better be equal. Those two better be equal. Those better be equal. And this better be equal to that. So let's run through and write down what we've got. The x cubed here better equal the x cubed here. So 1 equals a. Done. The x squared here better equal the x squared here. So 1 equals b. Done with that one. The x term here better equal the x term here. So 0 equals 4a plus c. And the constant here better equal the constant here, so 0 equals 4b plus d. And even this isn't very bad, because what's a? We'll get a 1 here, so 0 equals 4 plus c. So what does c equal? Negative 4. Plug in a 1 here, I get 0 equals 4 plus d. So what does d equal? Negative 4. So then we come back up at the top. Any questions here? Come back up at the top, and then we go through and we say, all right, this is ax plus b. So this is going to be x plus 1. And this one's going to be, let's see, c is negative 4. So this would be negative 4x minus 4. And there's our answer. Okay, and again, the only time you'd really ever want to do this is in a calculus class. Okay? In second semester calculus, if you were to try and do this problem right here, it's actually something that we call an integral. That right there is a calculus problem. And calculus in this format is very difficult. Calculus in this format is a lot easier. That's really it. Okay? So let's see, maybe in 2 years, for most of you, about maybe around right now, you'd be hitting something like this, okay? And you'll see partial fractions again. Okay, any questions? Sure? Okay, when is the test? Wednesday. Can you be gone on the day of a test? Please make sure you're here, okay? All right. Test shouldn't be too bad. It's just on those two sections. Partial fraction decomposition. If you can do this stuff and the stuff on the homework, test should be a breeze. Okay. Section 2.6, graphing rational functions, domain, vertical asymptotes, horizontal asymptotes, slanted asymptotes, x-intercepts, y-intercepts, all that sort of stuff. Getting a point on each one of the branches, stuff like that. And then something about parabolas. That's what the test is on. Okay? All right. I'm going to let you go early today. Have a great day. Have a great weekend.